title of this one is lecture number 7, and here I will talk about linear representation of nonlinearity, what you get in any input space. So generally I would be very specific regarding notation. So generally why I will take notation for response uh, or target or label, various name would be there, all those are synonymous. I won't change the notation. Either you call it response, label, or dependent variable. Various names are there, depend upon your understanding. X I will call it input variable, or you can call it regressor, or you can call it so simplest name is call it input variable. So if you're calling this one is input variable, so better call Y output variable. So Y would be output. Okay, and generally parameter I will call it generally another name of parameter, generally we used to call it weight in neural network. You might have already seen that. So W notation I will take it. Either you can call it parameter or you can call it weight. So these are the convention of notation that I will use throughout in this course. So be specific to this notation and don't confuse with any notation. You are free to change the notation as per your convenience, but I would, for general perspective, I will go with these three notation. Okay, so here when we are calling it the input space, that means that one is totally dealing with the input variable X. When I am calling it output space, that would deal with Y. Okay, and W, it is talking about parameter or weight, so that would define parametric space. So those things will come here. And you can call it weight or parameter. So all these three notation. So here nonlinearity generally always happens with respect to input. When you are taking a function like this way, so why you will call it a response, and you are taking function like y equal to x square plus 1, simple quadratic kind of thing. So definitely if you talk about a structure of this one, definitely a structure of this one, it is nonlinear with respect to input variable x. So that's why it is having nonlinearity in the input space. But if you try to model this one, then you can model it this one as a polynomial, because suppose you don't know the this explicit form and you try to model y as a quadratic form of this one. So what you will do, you will take better I don't have to change the notation of parameter. I should always take so I am taking w naught plus w1 times x plus w2 times x square. So you can observe here that actually it is having a nonlinear structure with respect to input, but linear structure with respect to parameters. That's why we call it, it is a linear representation of the response y. Linear representation we are calling it. It is all about that we have to learn W0, W1 and W2 from the given data set. It is all about that learning problem. Okay, so all these were about the notation convention. So coming to outline of today's lecture, first I will talk about I told that linear representation of nonlinearity in input space from the general perspective I will talk. Then I will go to talk further in a specific way that we will try to capture nonlinearity with respect to various bases. So various bases we will take. So among those bases would be simplest one would be polynomial basis. Then we will go for radial basis. Then we will go for Fourier basis. Among the Fourier we can go various Fourier kind of basis like truncated Fourier basis, cosine Fourier, sine Fourier. So many various basis here itself you can define it. Then we will go to discuss about sigmoidal basis. Then we will go to discuss about piecewise linear basis. It is also very interesting directly coming from numerical analysis. Also you can go for here in the piecewise linear, also you can go for a spline. Okay, so spline kind of basis. Then we'll talk about hyperbolic kind of basis. So various basis will come, all based on what kind of data you are having. Based on that we try to take such kind of basis. Okay, so all these are the outline. And coming to first part of this lecture here, that means talking about general perspective of linear representation of nonlinearity in the input space. So how you do? So suppose even response also you can call it signal. Suppose y is a response, and you are having in certain input space. Try to represent y as a yes. Am I audible? Any question? Anyone is having any question? Okay, fine. I'm going forward. Okay, okay, fine. So I'm talking about here linear representation of a function in term of basis function. So this one is the general theory. Then we will go for a specific. So a common choice for hypothesis function. That hypothesis function, what I call that, if you are having a response, but you don't know the explicit form of the response, that dependency of y in term of input x. So what you do in place of that, you try to approximate this one with some kind of, if you introduce some kind of modular structure through that, you say that that hypothesis function is our modular structure, and you can say that it is having a very specific kind of modular structure, and from there this structure we try to put in linear form. So this is the hypothesis function. We try to give parameterize it. So we try to parameterize it by introducing parameter as in term of linear, and rest of things would be in any form, whether it is non-linear, linear, quadratic, cubic, whatever, it depends upon situation. Okay, so a common choice for the hypothesis function f of x for a linear model is a basis with a general basis. It is a uh, what is a common choice, that it always involves some kind of basis, and that basis is having a collection of basis function, or that basis function actually what this basis function happens to be function of the input, or also you can say that this basis function is having another name, that as these are directly a transform version of input, so you can also call it these are derived features representation. And we can represent hypothesis function like this way: f of x, equal to linear combination of five 5k's, and that means n number of 5k we have taken, n number of 5k, those are actually basis function, and those are forming a basis. So in simple notation, all, so it is having n number of component. First component is phi naught. It is a indices, you can say that it is starting from 0. So phi naught, and it will go up to phi n minus 1. N dimensional situation I am taking it. Okay, so here all here this simply we are calling it basis, and these individual component we are calling it basis function. Definitely these would be function of x, that input, our input function of x. These are the basis function. Okay, and for we are taking for any arbitrary single sample, this notation we are taking. So here I have already mentioned that 5k, it is calling 5k, it is defined from rd to rn. D is the dimension of uh, input space, dimension of input space, or simply you can say that x belongs to uh, rd. X is the input variable which is d dimensional, dimension of input space. You can say that dimension of simply capital X I will write input space, and that means x belongs to RT, and that it is transforming to Rn, n dimensional, n number of component you are taking it, and they are getting n dimensional space. Okay, so that is the perspective. So here n number of component simply it is, so it is a function from Rd to R. So real value function, and n number of component you are taking, that's way I is a function from Rd to Rn, 5, and each component happens to be real valued function. So that concept you know from calculus, I think, and there is no big deal here. So phi, the basis is actually function from Rd to Rn. Okay, so often it is convenient to express this model in vector form. So vector representation always looks fine. So that's why uh, phi of x, that basis we are calling it, it is having n number of component. Each component is a basis, we are calling it a basis function. Remember that I am giving two name here. I am calling this one basis, and this component we are calling it basis function. Okay, these are real valued function of x, and that is a function from rd to r. Okay, and w we are taking, it is n dimensional vector whose each component is the coefficient of this corresponding basis function coefficient. So w is n dimensional uh, vector, you can say that, or simply this one is your parameter, n dimensional parameter. Okay, and with respect to this the representation, this linear representation take the vector form like this. F of x is actually dot product of uh, phi x basis phi x and with w. And you can remember that in linear model I have already told that, and these will form row of the what, row of the data matrix. These will come in the row of the data matrix. First that it depends on depends how many sample you are taking. If you are taking first sample, then uh, phi transpose of x1 will come as a first row. Likewise, if you are taking nth mth sample, then phi transpose xn, it will form the what, it will form the mth row, mth row of the data matrix. Simply these are forming the row of data matrix, this basis. Okay, and it can further explain like this way. Okay, these are the component of basis. That component we are calling it basis function, or simply we are calling that we try to derive the input as a derived feature. So derived feature also you can say that. Also another name also you can say that this feature map. Feature map also you can say that. There are various names, later you will come to see many name of the this basis function. uh, so right now I'm talking about it from general perspective. So here I will take one example. A basis function, what is happening, a basis function or feature map, it to project the input space to feature space, where the latent representation of the hypothesis function, it looks like linear thanks to what, those parameter or coefficient also you can say that. The more features, if we are having more features, that means if you are having more number of feature map or basis function, the approximation would be better, but problem is that that would be very expensive, and computational will be also very expensive. Computation will be expensive because dimension will increase, dimension of the feature space, it will increase exponentially. So uh, to define such kind of feature, few things I had already taken it here. These are the algorithm approach to approach. One approach that to define feature, we can introduce feature map with the help of kernel function. This kernel function about each point, we can select some specific kind of point that we are calling it xi, and in the neighborhood of that we can define kernel function. Another approach is that similar to covariance function also we can take it. It is very much similar to kernel function, and same covariance function we are defining with respect to x in the neighborhood of x. Okay, in the neighborhood of x we are defining. So these two approaches, so later I will explain these three. So these two technique and other things. Okay, now for simplicity I am taking very simplest kind of function. Suppose we want to learn this function, and this function of two variable bivariate function f, f. Okay, it is having two component x1 and x2. It is function of two variable. First component is this one, second component is this one. We want to learn this one, and we want to learn as a linear representation, or simply we want to represent as a linear combination of a few basis function. How we can do that? How so definitely it would be an approximation. So I have taken few approaches. So first approach, so in order to that means we want to introduce some kind of basis function. Suppose we want to take, also remember that we need to also smartly select number, how many number of basis function of feature map you want. Suppose here in this case we, for simplicity we want only two basis function. In that case this fx we want to represent as w1 times phi 1 w and plus w2 times phi 2. That means n is equal to 2 here. Intentionally we have taken it like this way, and even you can go for n equal to n like this way, various n, 3 4 5 6, depends upon your situation. But remember that your input space is what, r2. because it is function of your input variable. It is two-dimensional variable, so that's why input space is R2, and but output space, it will depends how many basis function you are taking. It may be R to the Rn, it may be R3, it may be R4, it may be R5. Simply call it, this one is the feature space, this one is the input space for this function. Okay, now we try to look linear representation of this one, and simply if you try to see, it is not linear, it is highly nonlinear structure. This function, if you try to plot this is talking about surface over two-dimensional plane. So if you try to plot it, definitely graph would be a surface, but can we get a linear representation? We will try to do that. Okay, through basis, some kind of basis. So here we are taking n equal to 2. The dimension of feature space we are taking, intentionally we have taken 2. That means we need to take only two basis functions. So one basis function we are taking phi1 equal to x1 and phi2 equal to x2. So two basis function we have taken. Why? Because here n we have already fixed it 2. So with respect to this, we try to approximate the actual function by linear combination of phi1 and phi2. Phi1 is equal to x1 and phi2 is equal to x2. That's why we are calling it, this one is the approximation representation of the fx, f of x1 x2, and it is coming as w1 x1 plus w2 x2. If try to see this one in the feature space, then it is a linear function, and graph you can see like this way. This one is your actual function, that is function of f of xy. Okay, function of xy, and these are the contour plot. So for better understanding of any surface, what you do, always you try to plot the contour as well. So contour plot always giving more insight to the function. Okay, here this one is the actual function, that one is given. Now here what we do, we have taken one basis function phi1 equal to x1 and phi2 equal to x2 we have taken. So these two are the basis function, and this is the feature space, this is the input space, and this is the feature space. Okay, feature space, in short I'm writing it fs, input space in, input is. Okay, so this one. So in feature space you can see that we are getting a linear approximation of this function. This is the linear approximation of f. So that's why we denote it by f cap. Actually it is a linear combination of phi1 and phi2. And here this approximation doesn't look good. In the small neighborhood of 0 0, a small neighborhood of certain point, we observe that approximation looks fine, but if you go away, then approximation is not good. So this, simply we can say that this choice of basis function is a very poor choice. It is not giving a proper approximation of the actual function. So randomly if you select any basis function, it won't work in ideal situation. But what you do, smartly you have to definitely your function will say that what kind of basis function you want to take. Something you have to look in inside the function, then definitely you will come to know what kind of suitable basis function we need to take. So here we are taking another set of basis function for even here, and we have taken 2, and now we are taking a new set of basis function. So first basis function is phi1 equal to, it is a square of modulus of x1 minus x1 star. X1 star means it is a fixed number, and phi2 is modulus a square of modulus of x2. So these two are the basis function we are taking. We can take any basis for any any kind of basis function. So definitely that must be function of what, input variable. That must be function of input variable. So that's why we are taking these two basis function. Now with respect to this, we can get an approximate representation of the function as a linear representation. We can observe that we can call it a w1 times phi1 plus w2 times phi2. That means it is linear with respect to w1 and w2. So we can say that this approximation is a linear representation of what we call uh, linear or approximation of linear representation of the actual function. We can say that if you try to take value of w1 equal to 1 and w2 equal to 1 as well, then you will see that this one is talking about same function f of x1 x2. Okay, that means we see this kind of situation. This one is the original representation, but here situation is changed. This phi 1 is not equal to x1. This phi 1 is what? This phi 1 is some kind of curve, but here it looks like linear. It is actually x1 with respect to input. It is a curve. So input of space is, this is the input of space, and it has been mapped to here. So with respect to input variable, this one is a curve, but here in this representation we observe f cap is a linear combination of phi 1 and phi 2 is what here, a square of modulus of x2. So this is the linear representation of this is the linear representation of f. And here you can see that this here f is nonlinear in nature, but if you try to see this function with respect to this basis representation, then deep down inside this function itself behave like a plane. You can say that it behave like a plane. Here it is behaving like a plane, but remember that here this space is no more your input space. It is a feature space which has been transform. It is a transform version of input space through nonlinear map. This map is, this feature map happens to be very nonlinear, so it looks little bit strange. Okay, and this one is the input space, and here representation looks linear. So this is the concept that same here nonlinearity can be captured by this linear representation. It is all about linear representation of a function with respect to basis function. Now, so here this representation looks very perfect. It is exactly matching with the actual function which happens to be nonlinear, but such kind of basis, luckily you will get. You have to be very you have to be very experienced in order to find such kind of suitable basis function to convert a nonlinear structure to linear structure. Okay, going further, in second part of this lecture, I told that I will try to capture nonlinearity using various uh, specific basis. So simplest one happens to be polynomial basis. First, I would like to talk about capturing of nonlinearity with respect to polynomial basis. So everyone know about what is the polynomial basis. So you are having input variable x. Then how can you can design polynomial basis? You can simply design by taking several polynomial of this one as a monomial. Take several power of x. So first simplest power is x to the power 0. That means x to the power 0 is what, 1. Then you can take next basis function, you can take x. The next basis function you can take x square, and likewise you can go up to as much as feature map you want. You can go up to that. It depends upon your situation, your choice, how many basis function or feature map you want, how many, what dimension you want to fix for the feature space. It depends upon your choice. So here I have taken it like one choice of basis function. I am calling it polynomial. In the simplest polynomial basis, polynomials are actually happens to be monomial. You can go for quadratic and other kind of representation as well, but simplest approach that here feature map or your basis function, it would be monomial. Better just a starting phase, take monomial like this way, that phi naught of x it is equal to 1, that we are calling it x to the power 0, and phi 1 of x equal to x, phi 2 of x equal to x square. Likewise x to phi n, it would be x to the power n. So all these feature map or basis function are what, these are monomials. That monomials means single, there is a single term of the exponent of x with exponent of power of x, simply you can say that. So like this way, this is the basis one choice of basis. Okay, with polynomial as a monomial as a basis function. Okay, so we will take few things, and what you do, we will take all possible combination, linear combination of this one, and with respect to each combination we can get a nonlinear structure. But that nonlinear structure is what, that one happens to be a linear combination of this basis function. It happens so like this. Here in left hand side we can say that we have taken several polynomial, like this one is talking about one polynomial, that this first basis function 1, then we are having x, this orange line is talking about x, then we are having x square, this purple line is talking about, purple curve is talking about x square, and like x cube and x to the power 4, that we are calling it quadratic or biquadratic. So we have taken five five basis function. We have taken here five basis function. If you take any linear combination of these two, you will get here in right hand side, you can observe that what this one is talking about one combination of these five, this one is talking about another combination, this one is talking about another combination, this one is talking about another combination, so this one is talking about another combination. So all these are the various combination or linear representation of these basis function, these five basis function. All these are, each one happen is a linear representation of this one, linear simply we are linear combination of these polynomial basis functions. Okay, so if someone is taking, suppose so, just if you suppose someone is noted down this data for this system, okay, and try to approximate this one through that data, then what that person will take this as basis and will take a linear combination and just optimize that problem, that optimize that minimize that error function, that criterion function, and through that you will see that your solution is coming very near to this linear combination. That means you are able to express this purple graph in right hand side as a linear combination of these basis functions. So each one you can say that it is a linear model of these, each one, this one. And now next question would be it depends upon data, what would be your optimal model. So optimal model that you need to optimize, so optimize some kind of error function or criterion function. So in right hand side each one represent one linear combination of these. So this we are calling it linear representation of any non, so you can say that all these are nonlinear things. So we try to get a linear as a linear representation of this nonlinear basis. Your basis nonlinearity is actually captured by the basis, and the basis what you want to introduce there. Okay, we will go another uh, thing that that suppose your response or label, it happens to be not continuous, it happens to be discrete in nature or label kind of thing. That means that problem is categorized, you can call it, it is a classification problem. So it is all about finding a in classification, all about finding a what, it is a separating hyperplane, or simply you can call it boundary line. So if you are willing to find a boundary line, then again you can introduce polynomial basis. So for simplicity we consider a simple data set that is already given here. I will produce that in one dimensional, we are taking one dimensional data set and it is having two classes, and these data set are not separable with a single threshold. We can't separate, you can look it into here like this way. This kind of data set we are having dot 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 cross 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 dot dot dot. So two kind of data set we are having. If someone is saying that we try to classify these two with a single line, then it is not possible. At least you need to introduce some kind of curve, then you will be able to separate these. Then how you can separate these linearly? So what you do, again apply polynomial basis here. That means what you do, introduce one transformation that transform all these data by x square, do a squaring of this one. So after do squaring it, that means you are introducing you are just introducing a quadratic feature map over the input x. Then due to that feature quadratic feature map, you are getting this kind of data set. Now easily you can easily bifurcate this data, classify this data into part. So this part is falling in, you can call it, suppose you can give minus one label and upper side you can give plus one. So there is a clear linear boundary or separating hyperplane, you can get it here, which will separate these two class of data. Why? Thanks to this polynomial basis, it is able to separate. So simply basis can introduce any kind of problem, whether it is a regression, classification, whatever, depends upon what kind of problem what you want to proceed with. You can always introduce basis in order to convert that problem into linear problem. So it is easily you can say that it is a linear problem now. It is highly nonlinear, because here in order to separate, what you do, you need to introduce a curve. Suppose this circular curve, you take it, then you can say data within this curve, that one is in one class, that we are calling -1, and which are outside, which we give a label +1. So linear separability is not possible here. But if you introduce one feature map, that quite nonlinear feature map x square polynomial map, due to that it has been transformed into in this form, and there we can see that a linear separability. So that's why basis is always giving a linear representation. Now I will talk about just one more example, that radial basis, or you can say that Gaussian basis as well. So another choice of basis function that we can call it a radial. The simplest radial basis is the Gaussian with center mu k and variance. You need to take variance as well, variance sigma k square. Okay, that means here kth basis function you can represent in the term of this Gaussian representation. Gaussian representation for k equal to 0, 1, 2, 3. You can go up to what dimension of the picture space you want. You can go up to that level. Okay, and here in the left we can see that we see several element of radial basis. These are the several various radial basis with different mean and different variance. Or some simple variance I have taken intensely 1. Variance is equal to 1 for each one. You are free to take anything. So variance is 1, but center is mu k, that one is changing. Here the 1 mu k is -3. Here -3 is coming here between here -3 is coming. Another one is having center -2, -1, 0. So various radial basis we have taken. If you take each possible linear combination, so one combination is giving this structure, another combination is giving this structure, another linear combination is giving this structure, another linear combination is giving this structure, another linear combination is giving this structure, then that means if you take various linear combination of these radial basis, you will get various several nonlinear structure, but that representation is actually linear. So that is the beauty of representation with respect to nonlinear basis. So other things we will cover in next class. I think it is already around 40. Now do we have time? Okay, it will go up to 2 p.m. time, I think, class time. So I would like to cover few more bases. Am I audible? Any question till now? Anyone respond? Anyone is having any question? No question. Okay, fine. I will go forward. Another basis I can take it sigmoidal basis. So sigmoidal is the very simplest nonlinear basis. So another choice of basis that we are calling sigmoid. The simplest sigmoidal basis, it will have the form of that phi k of x. It is defining by the sigmoid function of x minus mu k with again you can call it a it is not actually population deviation. You can say that it is a sample deviation with sample deviation, and here for various k we are talking, and here again you can define your the dimension of feature map as per your choice. I'm saying it is going up to n, and the sigmoid function it is defined like this way. That means sigma of a equal to 1 by 1 plus exponential of minus a. So it is, so graph is, it is having a s kind of shape. So when a is very less, near to minus infinity, then this will approach to 0, and when a is very big, then it will approach it vanish. So it will go to uh, s shape. It is making s shape. So maximum value would be 1. So the value of this sigma function, it lies between 0 and 1. It is coming like this way. S shape, simply S shape. Definitely there would be a stretch to that what we call it. Uh, it is trying to touch one here in right way, and trying to touch this what we call it x-axis when x is very negative, very negative. This situation, simply S situation is coming. That's why sigmoidal term is coming. And with respect to this basis function, so here we have taken various basis function. So if you took again each combination will give a nonlinear structure. But combination, linear combination, what we are taking linear combination. So each linear combination giving is just giving a nonlinear structure. So that means a nonlinear structure can be captured with the help of nonlinear basis function or nonlinear feature function. You can easily capture that information. So that is the ultimate aim of this class. Okay. Going further, this basis everyone might be aware of this one. In math 1 you might have already gone through. In math 2 also you might have already seen that this basis we are calling it Fourier basis. Fourier basis means if you are taking any kind of what we call it periodic signal, then always you can write that periodic signal as a linear combination of sine and cosine. Sine and cosine, what we are calling it in there, and the corresponding basis function we will call it either you can proceed with only sine or you can proceed with only cosine. And also apart from sine and cosine, what we are saying, because this kind of basis is very much suitable for only periodic kind of data. If you taking a data which is coming from some kind of periodic phenomena, then better you try to come with this basis, Fourier basis. And in the periodic thing you always encounter few certain quantity. What are those? We are calling it frequency, linear frequency, angular frequency, and another one phase. The phase, those are very important phase physical quantity. You need to be aware of that. So we have to take certain kind of uh, what we call it frequency, and certain what we call it phase as well. So if simply I'm asking what are the representation of phase till now, frequency you have seen till now, you might have already seen that if you are taking a cosine signal, you generally denote it by cos omega t, or here input variable is x, so I will call it omega time x plus phi. Phi is the phase. Okay, tell me this omega, what kind of frequency is this one? Anyone can say that what kind of frequency this omega represent? Anyone? Am I audible or not? Okay. Okay, then tell me, omega is what kind of frequency? You forgot. Omega is actually angular frequency, and actually there are two frequencies. One omega generally we are calling it angular frequency, and what we call it f. F is a linear frequency. So the relation between omega and f we can relate it by omega equal to 2 pi f. That's way in some notation of cosine signal or sine signal, you might have already seen the representation cos of omega x plus pi, or sometime you might have seen the notation cos of 2 pi f, 2 pi f x plus phi. So both notation are same, both are talking about same, but just it is all about frequency, what frequency you want to take it, whether you are taking angular frequency or whether you are taking linear frequency. So the relation you can get it like this way. It is very simple concept from physics, you can recall it all these for periodic phenomena. So one a straightforward approach is to choose a set of frequency. So that's why I am talking about frequencies that intensely. I haven't mentioned here angular or linear. You can proceed with anyone. If you know one, then you can convert it to other by this relation. You can easily convert, and you can take phase. Apart from frequency, you need to take phases as well to construct a basis function. How we are constructing a basis function like this way. So phi naught equal to, if you're just going for cosine kind of basis function, then uh, phi naught of x, it would be just 1. Phi j of x, it would be cosine of omega j x plus psi j. Omega j, again I am calling it that angular frequency, and psi j is your phase, and the relation I had already expressed. So you can take here j, the value of j you can go up to 0 to n. It depends upon what kind of feature of space again you want. So I told that. So all these are the uh, basis. what kind of basis function, you can, or you can go up to n minus 1. If you are willing to get n dimensional feature space, then you have to vary j from 0 to n minus 1. That means you are getting a n dimensional feature space. Then try to visualize the what each feature map or basis function. Remember that every time I am saying that basis function or feature map both are same. So here for various uh, composition of omega n psi, we have taken different what we call it feature map, or what we call it basis function, various. So these are the various basis function. And if you take a single linear combination of this one, that single linear combination will give this nonlinear structure. If you take another linear combination of these basis function, that will give this nonlinear structure, but it is actually linear with respect to this basis. It looks non-linear, but it is linear with respect to this basis, because this we are getting as a linear combination of this one. That same thing what you might have already studied in Fourier series representation. So that is the approach, that one linear combination is if you take various linear combination, you will get various linear models, simply linear representation. Each one is a linear representation of this basis function. So but if you try to see with respect to input space, all these looks with non-linear. Why? Input is what? Single variable x, and this so with respect to input, it looks non-linear, but with respect to parameter or coefficient, it looks linear. It is with respect to parameter, it looks linear. So that's why I told that nonlinearity we can capture with the help of some specific basis. So if you take different basis, you can get different you can able to capture different kind of nonlinearity. So other things we will cover in next class. And regarding attendance, just go and mark your attendance there in the comment box. And if anyone is having any question, you can